Alright, we'll make this the last one of this series, but let's really be clear that at this point, as we get into using more and more tools, you need to have solid your ability to use vectors just as a general rule, force vectors particularly. And so you're going to be doing a lot of trying to figure out the reaction to things. So I'm going to draft something out here. It's going to be my least. Alright. And I'm going to tell you, I'm going to put something out here, just a little tiny piece of steel or something out here, and I want to see whether you can do this for me. Make this a line of force. Can you believe, see, or know that this, let me give this for the first time some value, we'll give that 5 pounds, and we'll give this distance here 5 feet. Can you see that this 5 pounds placed out there and this same 5 pounds placed here, but also with a twist or a torque of 25 foot-pounds is the same thing? Can you see that the definition of equality between systems of forces, equality between systems of forces, is equal forces and equal moments? And if you think about that, if this is the point here, this force obviously is 5 pounds in this direction, but it also has a moment arm of 5 feet, meaning that it has a torque of 25 foot-pounds, which is the same as this force, which is parallel to this one, but also in addition a torque there, more or less a torque, which could be, of course, could be something like 25 pounds, which would be a lot more than that, 1 foot apart, or 1 pound 25 feet apart. This idea of when you're going to be cutting the beam, you're going to essentially get what's there, a set of basically equal and opposite non-concurrent forces and stresses, which is more or less is a moment. Right? The internal stresses in the structure. So, realizing that you can slide a vector up and down its line of force and not have to do any kind of shenanigans or computation with the moment, but when you shift a vector, you have to replace its shift basically with the area, if you would, defined by that shift. That area is 25 foot-pounds, therefore it's going to be put here as 25 foot-pounds. So learning how to go about adding vectors and sliding vectors that way will become relatively useful, especially when you start getting to the point where you're looking at the world like this. You have some structure, as you've seen at least in the exam for reactions. You have some structure that might look something like this. See if I can draft my beam. And I'll go ahead and make this a frame. In other words, these are all solid here, welded up. And if in fact we then have a force applied right here, but you're interested in what that force is reacting, or what this structure is reacting to right here, you can go about that problem many, many different ways. But one way is to just kind of go ahead and draw this here, right? And basically, or do it this way. Erase this out here. I can go ahead and draft here. I'm going to replace that reaction right there with a torque, a tension, a bending, and a shear. And then realize out over here I just have to more or less translate this to there and replace that with this and this, which means these two have to add up to be the opposite, and this has to be the opposite of that. And so this concept of adding a bunch of different vectors, right, you can either do it by superposition or by simplification. And when you finally simplify all of your vectors into one force vector here, yeah, I'll be there, hang on, and then shift it over to here, you replace that single force with a force couple at the point, and you can remember that the internal reactions are the opposite of the external forces.